So in this video, before talking about a new strategy to determine whether certain infinite series is convergent or not, we would like to look at all the methods we learned in the last couple of videos. Please look at the method one by one. It would be beneficial to you to see the disadvantage of each test, because usually for this chapter, one test is used to apply specifically to certain type of problems. No test can be used to solve all problems, and that's the tricky bit in this chapter. And the fact is that you can look at the series one by one. And you see, for the first method, which is the geometric series test we learned, it only works well for geometric series. And of course, there are so many non-geometric series we look at already, and we understand the geometric series cannot be used to solve those problems. And let's look at the second test, which is the M-term divergence test. It can only be used whenever the limit of the individual term is non-zero. We know it is divergent. However, it's not going to work well when the limit of the individual term is zero. And let's look at the P series. The P series is convenient for 1 over n to a fixed power P. And we understand the criterion to determine whether it is convergent or not depending on P. But it only applies specifically for the P type, right? And there are so many series which are not P series, of course. And let's look at the integral test. It is actually quite useful, but the fact is that sometimes the integral is hard to compute. We don't want to spend too much time on doing the improper integral calculation. And also, it only works for the infinite series where all the terms are positive. You see, this condition is important. And the comparison test comes from the last two videos. We have looked at two different versions of comparison test, and it usually works only for all the positive terms inside the infinite series. And if you look at all these tests we have seen, there are still many infinite series which you cannot understand based on just these five methods, right? For example, we can easily pick up some series like this, you see. The terms are positive, negative, and so on. It is called an alternating series. So we cannot directly use the integral and the comparison test. And of course, there's a big chance it is not a P series. And there are many examples like this, which is not geometric. And even worse, if you look at the individual term, maybe the limit is actually zero. So you cannot say anything about this. And this video is all about this type of alternating series. And let me write it down here in the next page. So please look at the current page here. I call it the alternating series test, which is very useful whenever you see an alternating series like this. And whenever such an alternating series satisfies both conditions, so you have to check these two conditions on your own. If they are okay, we understand that the current alternating series is actually convergent. And let's look at the next problem. Please look at the current alternating series, and as I emphasized for many times already in the recent videos, because you have learned so many different series tests, you have to go through in your mind whether the earlier method can be used to apply to the current problem. And actually for this alternating series, the answer is yes, without using the current alternating series test. I think we can just solve it by the earlier method because of what? Because as you can see, there's a fixed ratio among the terms. The fixed multiplicative ratio that you can use to multiply to the first term to get to the term is minus 1 over 2. Same for the second pair and same for the next pair. So it gives you a sense that for this alternating series, the ratio is minus 1 over 2. And the fact is that it is a geometric series with the first term, we usually call it A, which is 1. I'm just picking the first term here. And the fixed ratio is actually minus 1 over 2, right? And let's apply a geometric series test. And we can take out the negative sign after using the absolute value sign. So it becomes half, which is less than 1. And we understand that our current series is actually convergent. And more than that, a geometric series is actually the best when it is a convergent series, because we actually understand that the value it is approaching is determined by the formula A over 1 minus R. And in the current case, it's the same as 1 over 1 minus open bracket minus 1 over 2 close bracket. So this answer is actually the same as 2 over 3, right? So this 2 over 3 means that if you keep doing this summation process forever, this value is actually approaching 2 over 3. But this problem is based on the fact that it is alternating and it is geometric, right? And let's look at other examples where it is an alternating series, but it is not geometric. So please look at the current problem. If you try to expand it, you can notice that it is an alternating series because usually when you have a term like minus 1 to the power n, or something like minus 1 to the power n plus 1, we understand that this term represents the fact that you have to change the sign whenever you look at the next term. For example, like the current case, when you try to expand it, it's actually the same as 1 minus 1 over 2 plus 1 over 3 and so on, minus 1 over 4 and so on. So it is of course an alternating series because you see it's plus, minus, and so on. So we have to apply the two checks here. The first check is that we want to see whether this term, when you take the limit n goes to infinity, it is 0. The answer is yes, because conceptually it is 1 over infinity, which is 0. So the first condition is satisfied. How about the second condition? The second condition is that we have to look at this sequence. If you think of it separately as a sequence of numbers, I think it's obvious that this is a decreasing sequence because of the fact that the top, you see, the top is a fixed number 1, and every time you go to the next number, you have to increase the bottom, the denominator, right? And it's obvious that it's a decreasing sequence, so both conditions are satisfied. So I can claim that by the alternating series test, our series now is actually convergent. And let's look at another problem. So please look at the current alternating series, and once again, whenever you have the term minus 1 to the power n inside the summation notation, we understand that it must be an alternating series. So we can directly look at the two conditions we have. The first condition is about taking the limit of the term we have here, but I think because it is rational functions in n for sections, whenever n goes to infinity for such things, we can just look at the dominating term with the highest power. So this limit n goes to infinity for n divided by 4n is clear. So the answer after cancelling the common factor n is actually 1 over 4, right? Which is actually non-zero. And please think about it here. I don't think we need to check the second condition. We don't need at all. Because this fact, the limit of this term is non-zero. It's basically considered quite close to the n-term test, right? And it gives us a sense that whenever the condition 1 is false, we understand that our series, which is alternating, is actually divergent. So this is by our alternating series test. And anyway, this problem is fairly easy. When you check the limit of this term, it is actually non-zero. Then we can claim it is divergent. And let's look at the last problem here. So please look at the current problem. We understand it already that it must be an alternating series because of this sign change term. We can call it an alternating sign term. And anyway, by the alternating series test, there are two conditions to check. The first one is about taking the limit of the term inside. You see, we can just keep the highest power term top and bottom. So we can cancel out two copies of n, top and bottom. After canceling two copies, it becomes 1 over n. And we are taking limit n goes to infinity, so it becomes 0, right? So at least the first condition is fine. How about the second condition? We have to check whether it is a decreasing sequence when n goes to infinity. If you just look at the first couple of terms, so let me compute it here. So you see, if you just look at the first couple of terms, actually it doesn't look like it is a decreasing sequence because obviously the second term 4 over 16 is bigger than 1 over 9. And actually, the fact is that the third term is also bigger than the second term. And after the third term, it looks like it is decreasing. But we never know. Maybe it will increase again later, right? So to confirm that it is actually a decreasing sequence when n goes to infinity. So what we need to do is this step. We have to check what's happened to the term when n goes to infinity. You see, mathematically, numerically speaking, when n goes to infinity, we can drop the term with the smaller power. So, which means this fraction is very, very close to the fraction on the right-hand side, which is n squared divided by n cubed. I can cancel out 2 copies of n to get 1 over n, right? And this approximation means what? It means that when n is very, very large, we expect that this fraction half is very close to the fraction 1 over n, and of course 1 over n itself is always decreasing, right? So let me write it down here. Because of the fact that 1 over n is always decreasing, we can claim that at least for n very, very big, our fraction is increasing. So it means our condition 2 is satisfied, right? And it means by the alternating series test, our alternating series is actually convergent. And that's the end of this video.